Astronomer Bill Hartmann has spent his life studying the events of the early solar system.
The record of the very first part of the Earth's history, all of that is wiped away on the Earth itself because we have erosion and rain and continental drift and continents colliding and mountains coming up and so on.
But all is not lost. There is a record of Earth's earliest days, just not on Earth. It turns out the best place to look is on nearby Mercury and Mars. Their surfaces have barely changed in over 4 billion years, providing us with a unique record of events in the very earliest days of our solar system. They're dotted with ancient impact craters.
You start looking at those craters and you discover that there are not only 100-mile craters and 200-mile craters, there's 600-mile features. I mean, some very large objects.
These craters paint a picture of an intensely violent period, of a solar system littered with cosmic debris, where millions of asteroids and comets smashed into the young planets. In the thick of this all-out assault, the Earth too must have been struck.
It was a window into the early history of the Earth, and it made us realize that the Earth itself has had this tremendous history of impacts, enormous impacts that could have really damaged the whole planet. It got people thinking about what would be the effects of giant impacts on the Earth.
Hartmann realized that it wasn't just small asteroids hitting the planets. There were much larger objects too. And the larger the object, the more dramatic the consequences.
So the impact process, it's a wonderful kind of paradox. On the one hand, the small impacts tend to make everything the same, millions and millions of impacts averaged out, but the big impacts give individual personalities to the planets.
Take our planet, tilted on its axis at 23 degrees, with a nearby orbiting satellite, the Moon. We used to think that they'd been born together, until Hartmann proposed a radical theory. The Earth had been hit by something the size of another planet, creating that tilt and the Moon.
The key to our idea was that as the planets grew, you had the finished planets, but you still had leftover bodies. If one of those crashes into the Earth, just as the Earth has finished forming, that can blow out material from which the Moon could form in orbit around the Earth.
Picture the scene. The newly formed Earth hurtling round the Sun, and loads of other planets doing exactly the same thing. Including this one, Theia, about the size of Mars. It was orbiting the Sun at exactly the same distance as the Earth. The two planets were on a collision course. Theia hit the Earth at 25,000 miles per hour, with the force of billions of megaton bombs. The impact ripped off huge sections of the Earth's crust. Billions of tons of debris blasted into space. A ring of red-hot dust and rock formed around the Earth. Over the next 100 years, the rocks and dust slowly clumped together into a ball 1/50th the size of Earth. We call it the Moon. When Hartmann suggested the idea in the 1960s, people found it hard to accept.
Scientists were thinking of everything in terms of slow geologic processes, one grain of sand at a time, wearing down mountains. To think of something as colossal as the moon forming as a result of a single event was hard for people to swallow.
But then Hartmann got the first real clue that his theory might be true. The Apollo project.
That's one small step for man, one giant leap for mankind.
American astronauts made 6 visits to the moon. They explored its surface, drove around its craters, and brought back 840 pounds of moon rock. For the first time, scientists could find out what the moon was actually made of. The lunar samples had a remarkably similar chemistry to the outermost layer of the Earth's crust. To most researchers, it was an interesting discovery. But to Hartmann, it was vital new evidence.
So you have crustal rocks, you have rocks on the surface, and a big impact comes in and blows all those crustal rocks away. And that material goes into space and forms the moon.
Many scientists were still skeptical. They just couldn't see how a massive impact could create the moon and the Earth as they are today.
I actually had people telling me we should exhaust every other theory first because this was such an outlandish idea.
It was a chance meeting at a conference with astrophysicist Robin Canup that gave Hartmann the breakthrough he was looking for. She was using computer models to study Saturn's moons.
Bill Hartmann came up to me after my talk and asked me, have you ever thought about applying your models about how moons form within and near Saturn's rings to the origin of the moon? And I said, no.
So she tried it. Canup used modelling software to recreate the early solar system. Then she plotted a planetary collision of the kind Hartmann was suggesting.
So we're 4.5 billion years ago at the end of the Earth's formation. And we're in space, and we're watching as a small planet, the planet on the right, is about to hit the young Earth, represented by the larger planet on the left. The collision takes place, and as we see it hits in a glancing blow. And you can see the impactor is completely destroyed by the collision.
Thea, the impactor, is annihilated. Earth survives, but only just.
Now, this collision is incredibly violent, so violent that there's enough energy to completely melt the Earth. And in fact, at the end of this impact, the Earth is surrounded by an atmosphere of vaporized rock.
Trillions of tons of debris blast out into space.
Here we see part of the impacting planet sheared out into this long arm of material that produces a disk that we're seeing almost edge on in this view. And it's from that disk that the moon later coalesces.
Canup's model demonstrates that the moon was probably made of debris from both Thea and Earth. It explains why those moon rocks were so similar to rocks from the Earth's crust.
So I actually called my colleague and said, you're not going to believe this, but I tried this Mars-sized impactor case with about a 45-degree impact angle, and everything worked. And he said, you better check it again. And so I did check it again and did many more of these simulations, and sure enough, that type of impact is the one that gives us the Earth-Moon system today.
Canup's work was further evidence that Hartmann's radical theory might just be right.
So it was very exciting as Robin did her models and they started to say, yes, there can be moon-forming debris left in orbit around the Earth, and the moon would form from that debris.
I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.
Columbia, Columbia, this is Houston, AOS, over.
Houston, Columbia on the high gain, over.
Roger, the EVA is progressing beautifully. They're setting up the flag now. I guess you're about the only person around that doesn't have TV coverage of the scene.
That's all right, I don't mind a bit.
They've got the flag up now, and you can see the stars and stripes on the lunar surface.
Are you getting a TV picture now, Houston?
Neil, yes, we are getting a TV picture. You're in our field of view now.
I'd like to evaluate the various paces that a person can traveling on the lunar surface. You do have to be. All right, you do have to be rather careful to keep track of where your center of mass is. Sometimes it takes about 2 or 3 paces to make sure that you've got your feet underneath you.